oxidation reactions. So oxidation reactions. So first of all, let's just define this, because in general chemistry and oxidation is going from iron plus 2 to iron plus 3. In organic chemistry, it's a little bit different. And we're going to think about alcohols because that's what's going to be most relevant to what we're doing now. So you can imagine 3 different types of alcohols and their substitution to start with. Primary, secondary, and tertiary. So this is going to be a little boring to write all this out. We'll do it. So how about 2R groups? It's pretty poorly drawn. And last, how about 3R groups? Just to review this language, since this is going to come up over and over again. So now let's define what an oxidation reaction would be. Let's start with that primary alcohol. So considering an oxidation reaction, which I'm going to just put a generic O in brackets, meaning oxidation. In organic chemistry, an oxidation reaction would be going from that primary alcohol to an aldehyde, for example. So that's an oxidation reaction. And one of the key things is that with a primary alcohol and an aldehyde, we can actually have a second oxidation reaction that's going to go from an aldehyde to a carboxylic acid. The definition of oxidation in organic chemistry is a little more convoluted. Not necessarily just the addition and subtraction of electrons, like it would be, say, for iron plus 2 to iron plus 3, but it actually has to deal with the removal of hydrogens and replacement of other atoms. We don't really care about that right now. So those are the oxidation reactions we could have, say, from that primary alcohol to an aldehyde and a carboxylic acid. Let's do the same thing with the secondary alcohol. We could remove one of those hydrogens and end up with a ketone. Sorry, I'll make that a little bit more clear. The double bond oxidized to a ketone. So going from a secondary alcohol to a ketone is an example of an oxidation reaction. And what you'll notice is in each case, we're removing a hydrogen. So if we go back to the primary case, we have 2 hydrogens here. Let's just say we got rid of the bottom one, and we have our aldehyde. And then we took off that next hydrogen to form the carboxylic acid. For the secondary alcohol, we removed this hydrogen, and we formed a ketone. We have a problem with the tertiary alcohol. We have 3R groups. We do not have a hydrogen that we can remove. So if we were to try to carry out an oxidation reaction here, there's going to be no reaction. So now let's think about a mechanism for these oxidation reactions. And there's all sorts of different mechanisms, different reagents out there. We're really only going to consider one here. And to start with, I think it helps to show a common mechanism. This might be confusing at first, but there is a reason behind this. I'll let you be the judge of that, but hopefully the goal is there's a reason behind this. Common mechanism is to introduce a good leaving group. And the goal here is to connect this back to organic 1 when thinking about elimination reactions. So let's use some generic nomenclature here, and let's have this secondary alcohol, just to make it a little bit easier, with this, so our hydroxyl group. And let's say we're going to have a reagent that's going to introduce a leaving group. So Lg is our leaving group. It's where the naming gets a little bit weird here. So what we're going to do is we can imagine having this attack, kick this out, forming a species now. This is all the same. O here. I'll put the hydrogen on the other side, so it's a little easier. Here's our leaving group. And now we have a formal charge on this oxygen. And let's have our A, which is just going to now take that proton off here. And so now we can rewrite a little bit bigger here. It's O leaving group. So now we have our good leaving group. And this is the key step. Now, if we had something in our reaction that can act as a base, B, with some electrons on it, maybe even with a negative charge if we wanted. We could have this now take off a proton, move these electrons here to form the carbon-oxygen double bond, and then kick out our leaving group. And the key thing is that this should hopefully look like an E2 reaction back in the good old days of organic 1. And what this is going to give us now is R, carbon R, with the double bond. So what we've done is we've turned our alcohol over here on the left to a ketone. Secondary alcohol oxidized it to a ketone. And at the core of this reaction is an E2 reaction. It's E2 reaction, where we're taking a proton off, forming now, instead of a carbon-carbon double bond, like what we've been seen before, it's a carbon-oxygen double bond, and the leaving group is leaving. So carbon-oxygen double bond is the difference, but mechanistically, it's very similar to what we've seen before. So that's the general mechanism. Now, let's bring in a little bit more chemical detail, but the idea is the same. So it's going to look more complicated, but the actual mechanistic details are going to be essentially the same. And this is the only reaction that we're really going to consider. I'll slide this up and try to leave this here so we can see it for parallel. And I need to first of all introduce a reagent. So let's just put a line here. So a common reagent, and this one gets a little bit confusing sometimes, is chromium trioxide. Or chromic acid. And you see these used interchangeably. This together, these are known as, especially the chromic acid, is known as the Jones reagent. Chromium trioxide is chromium with 3 oxides, and the oxidation state is chromium 6. Chromic acid looks like this, and it has an oxidation state also of 6. It's the same thing, and this is usually in sulfuric acid or in water. So a bit of the chemical detail is that you cannot just get a bottle of chromic acid, take it out of your acids cabinet. You're going to use chromium trioxide, and you'll mix it together with sulfuric acid and water or another species, and you'll end up with this chromic acid. Now, what's actually involved in the oxidation reactions could be a mix of the two of these, and I'm going to draw the mechanism using chromium trioxide, really solely because that's what's in the Sorel textbook, just so that we're not confusing things. So let's now consider that reaction above with the generic group, but now using chromium instead. So we'll redraw our secondary alcohol. This time I'll put the hydrogen over on the other side, since that's where it's going to end up. See if I can get this to actually connect. And CrO3 now, instead of leaving group. I'm sorry, let's make this look a little more geometrically correct. Chromium 6. So in the first step, just like above, I had this attack, and let's move electrons up onto one of these oxygens. So we'll just move it up here. So we're going to form a new bond between our oxygen of our secondary alcohol and that chromium. So O minus. And we have here O plus over here. This is still chromium 6. Now there's different ideas out there perhaps in terms of how these proton transfers happen. Do they happen simultaneously or individually? In the end, you can imagine water taking a proton off here, protonating here, and so on. I don't like doing this, but just to be consistent with the textbook, I want to show this just in one step. So we're going to take a proton off and move these electrons onto this oxygen. In a way, this is kind of the lazy way to draw it. So now we have our oxygen chromium OH that we have here. Okay, and then this is still chromium 6. So now what we've done actually is we've introduced a good leaving group with this chromium species. And so I'll make this a little bit bigger again here. And let's compare it to above. So going up to the upper right, we have our base, slide it down just a little bit, take a proton off, form our double bond, our carbon-oxygen double bond. And the leaving group that's cut off there in the top is going to take off. And this is our E2 reaction. So let's do the same thing, but now in a little more complicated way with this chromium species. Let's have electrons in this chromium-oxygen double bond take a proton off. Let's use the electrons in that carbon-hydrogen bond to form our carbon-oxygen double bond. And then last, let's move the electrons in this oxygen-chromium bond onto the chromium itself. So a lot happening in that step. But this is, again, it's essentially our E2 reaction. So let's see what this gives us. So now let's draw R, and we ended up now forming a carbon-oxygen double bond. So there we have our ketone plus chromium. This is the top oxygen. This is the one on the side. And we're going to end up adding a proton to that other oxygen. So we have something that looks like this. And then last, if something gets oxidized, something else has to get reduced. And what we ended up doing is remove those two electrons over here. I'll highlight them. In this oxygen-chromium bond, we put those electrons right on chromium itself. So chromium actually gets reduced. Chromium 6 to chromium 4. And so what we've done here is we've gone from, I'll go back out a little bit, our secondary alcohol to a ketone. So we've oxidized our secondary alcohol to a ketone, and we've reduced then the chromium trioxide in this case from chromium 6 to chromium 4. Now, as mentioned, a lot of times, I see in the textbook they actually show the mechanism for chromium trioxide, but then most of the time in the reagents mention chromic acid here. So in terms of just writing out the reagents, you can use those interchangeably. And in actual reaction, it's probably a mixture of the two. You use the chromium trioxide to make the chromic acid. One last bit of story time is that I actually